All right, welcome. I hope you all guys had a nice tea or coffee or a nice breakfast and you're just not too heavy, like ready to go. Today, we're going to talk about tutorials. We're going to go through a software as well. And also we'll have some fun activity later on, which is probably, this is the worst room for that fun activity, but we're going to do that with locksmithers. So you learn how to use that. I'm afraid we won't have enough time to cover both tools. So I posted them both online. They're available, the tutorials and the download links. During the break, I asked you to install one of the tools. Because we're in a computer room, I think they're already available on the computers. So you can just log in with your credentials and just get things going. But that is the plan. And we're going to solve problems. Today's problems are going to be very easy, but at the same time confusing, because there is a lot of terminology when it comes to lighting and daylighting, which you essentially need to know. But for the sake of getting an A+ as part of this course, you don't have to know every single difference about them, like what's this kind of surface, what's this kind of emitting surface, right? So you just need to know how to solve the questions. And that's it. Later on, if you want to become a lighting specialist, which is quite a profession itself, it's a career actually. You can just dig deeper if you want. Something I recommend is that today's tutorial, we're going to solve the examples, but try to either stick to the symbols or stick to the definitions, because then it might get confusing. And that is from experience. I passed this course myself. It was confusing, and it's also confusing for the people who are learning it for the first time, or it's your first time going through the course. Starting with isotropic. What's isotropic? It means emitting in all directions. For questions that we are solving, you will be seeing this term a lot. Essentially, what it means is that it enables you to solve the question. Otherwise, you are going to be dealing with a lot of different components when it comes to lighting. The first question is the lamp suspended above the floor of a very big room. The luminous intensity is shown in the figure. Assume that the unit is candelas, right? So that's something you need to assume. You can also see the small symbol right on the bottom right corner of the photo. You need to find the location of the highest illuminance measured as X meters from the point immediately below the lamp and the illuminance magnitude. Now, how many of you are familiar with this? This is a chart. Number one thing, well, Farzan, that is obvious. This is a chart. We engineers, we love charts, right? We just say, how can we make the coolest charts ever? This is one of the coolest charts ever. And you can see there are two different types of line here. One are these lines, and one are these radial lines. And then you have this hash area in between. This is a source of light. Okay. And what this shows is the light profile. You're like, Farzan, what is the light profile? A light profile shows how the lighting fixture will be lighting up your space in the simplest terms. Okay, now you'll be like, that kind of sounds crazy. We always want a light that just lights up the space under. That's what we have seen so far. True, but remember, if you're working in the lighting industry, there's also museum design. There's also urban design where you might need half of the light at the bottom, half of the light on the top. Okay, which we'll show you in a second what that is. But before that, you see how the light is distributed. So this is the hanging lamp, and this is how the light goes around. It does not necessarily go in all directions, very bottom. And the very simple question for you is, where do you think you receive the highest amounts of light?
Right under.
Right under, knock on the table for Daniel. Amazing, Daniel, right under it. And why is that? Because these radial lines that you see on the graph, these are the candelas. And they are the highest when it comes to the bottom. It's around 1100 there. Right? Now, if you are a picky person and you like to be Farzan, I suspect what you're saying is not correct. You're correct, because this light at the bottom curves a little bit back in. So the highest one is, of course, a little bit towards the outer side. Right? But for the sake of solving the question, we're going to be going with 1100. Now, I have this habit of showing everything on the screen by my hands, but because we're going to post this, just give me a second to annotate this. So these are the candela lights. This is where you will receive the highest, and because it curves in, essentially the highest is a little bit to the right and a little bit to the left. But for the sake of this question, we're going to solving this. The rest of it is a guessing game. This is going to be about 1100. Any questions? Okay, before we progress to solving the question, I want you to grab your phone and just the computers in front of you in this room. I want you to search lighting profiles. You can also call it, I think it's called IES profiles. That's like the more lighting engineering term for it. And IES is, I don't know, International Society for Lighting Illuminance or something. I'm not sure, to be honest. And you technically just need to look at the images and see what type of profiles are available. Did you get a chance to find it? Crazy lights, right? Some of them are even branching out when they're going, right? So based on your experience and what you need to solve, that's what you need to get going. All right. Now here comes the question. These questions, the most important part is that you understand what you're trying to solve. The rest of it, similar to everything else, we're just plugging in the numbers. That's the equation that we need to use. V equals to I divided by square root of V. Plug in everything, you have the distance, you have the candela that you guessed, and you get the final answer of 68.8 lux. Now, for the second part of it, which I want you to do it later on at home, and if you can't solve it, come back to me. Try to solve it as a matter of X meters for point P. We know how to calculate directly under. I want you to later on solve it for point P. We'll have example of how you do it later on in our tutorial. But for now, just remember, we want you to solve that. It's just for your own curiosity and get things going. You have the I, you have D, plug in the numbers. And this is what you're going to solve at home. We calculated for here. All right, that's the first question. Any questions so far? Your Faisal, like it's easy, tamam, huh? No, it's not that easy. This is just starting. So this was the first question. For those of you who don't know what tamam means, it means like finito. Example 3 is the top half of a 1 meter diameter globe is silvered with a reflectance of 90%, while the bottom half has an absorptance of 25% and a transmittance of 75%. At the center of globe, you have the 100 candela isotropic lamp. You see it, notice that term, isotropic, popping up everywhere. You want to find E, M, L, and I in different locations. Now, I'm not reading all that right now because we first need to visualize. As everything else in this course, first visualize. Got the globe. This is not, the blue light is not the light itself. It's just to split it in half. Okay? You have the upper part of it and the lower part of it. Now, I want you to take a look at the top left of the screen where you can see reflectance, transmittance, and absorbance. The sum of these three is always equal to 1. Right? Always equal to 1. The question is giving us that you got a reflectance of 90%. Probably you have something inside the globe so that it increases its reflectance. And it gets reflected, and then you have the transmittance of 75% getting out of it. And you got an alpha or absorptance of 25%, which is absorbed by the globe. And you got a point light, an isotropic lamp, 100 candelas right in the middle. And we want to find E. The first step, you want to solve the question is to figure out how much lumens you're receiving everywhere, right? And how do you do that? We essentially calculate it from this equation. That equals to 4 pi, the 100 candela that you have, right? That's how the entire globe. What color do you think we should pick for annotating this? Green? Yellow? Right. Okay, green is not bad, not bad, not bad. Okay, this is the equation. You got the pi, you have the 4 there, and you have essentially this here. You multiply all that, you get this 400 pi lumen. That's how much you got in the globe, right? You go back to the jargon, you see that we have an isotropic term, meaning equal in all directions. What does that mean for globe? It means you got the blue line divided by 2. You get 200 pi lumen up there and 200 pi lumen down. Does it make sense so far? Okay, very good. The upper side of the globe, you got the 90% reflectance. Why do I need to multiply it by 90%? Because the question is asking me to solve things for inside of the lower hemisphere. So we're calculating things for this point right here. Okay, I want to see how much of this light is reflected back to this point. 180 is the final answer because of the 90% reflectance. So out of these 200 pi that you have for the upper side, 180 of it is going back down. You sum that up with this 200, that's going to be 380. Any questions so far? Do not feel shy. If you did not get it, just ask and I will explain it again. All clear? All right. And that's essentially how you get this question going for you, right? Now, that 380 that we found is the key. Okay, this is working. Is the key to everything. Because to calculate E, you have this equation. That luminous flux is that 380 that we found, and the rest of it is just history. You just need to put the A there, calculate everything for globe, and plug in the numbers. You get this final number of 760 logs. Questions in lighting are all about you interpreting the question, getting the numbers right, and then just plugging things in. That's it. And then later on, you will see it's also important about understanding what alpha and beta are for calculations. But for lighting, these are just 2 things. The rest of it is equations, plug in the numbers. Any questions so far? All right. Sorry, this is going crazy. It's right now out of my control. Right. Right. Annotation tool is really annoying. But we need to find M and L, the next one, the luminance, excitance, and luminance. Very simple, very easy. All you need to understand is this part and this part. Okay. You have the numbers. The only important thing is that you remember there's a tau here. Multiply that tau thing. And I assume that you remember that tau is transmittance given by the question. Once you rearrange everything and solve the final one, you're going to have this 570. For the other one, it's the same. You plug in the values, and this m is coming from this m, which you just calculated, and just divide it by pi. And then you got the final one. One is lumen per square meter, and one is candela per square meter. So literally plugging in the numbers. Now, all right. This is where it gets a little bit tricky. The rest of it was plugging in numbers. Now you want to calculate luminous intensity directly below and from a far away distance. When it comes to calculating lighting questions and you have the light fixture or the surface of the light fixture, surface has a normal, right? And normal is a line perpendicular to the surface, right? Alpha is the viewer's eye directly below that normal. And where this is cos alpha equals to 1. Because essentially you don't have any distance or anything here. So this is like 0 degrees. And that's how your cos alpha becomes 1. The rest of it is solving this equation. And this equation has an AP, which is super simple. Plugging in the values P, R2, and the cos alpha, which is 1. You multiply everything, you come up with this final answer. And once you have that, plug in the values, you get this 142 candela. Just remember that that L is from the, sorry, it's not working very well. Anyways, that L thing is from the previous thing that we saw, from the previous part of the question. This is 181. Any question? Yeah, I'm recording it and I'll be posting it. All right. This is probably one of the most interesting questions, my favorite question, honestly. Perfectly diffusing panel for a tall 45% is viewed from point A. And the luminance of the panel viewed from A is 500 candela per square meter. You need to find luminous intensity, E, luminous flux, left side, and leaving the right side of the panel, and E on surface B. So A, B, C are all dealing with this part of question. And then you have the last one, D, which is dealing with this part of question. Right, there you go. We want to find luminous intensity. And you remember the normal of the surface. This is the surface normal, which is like 90 degrees out of the surface. Okay. The viewer is at point A, which means the alpha is 45 degrees for us. These are all given by question. Cos alpha is 0.7. But I have a quick question for you. And that is why are we multiplying the surface by cos alpha? And the answer is on the board. Can you put it in simple terms? What does it mean? Yes.
Off-center is zero. So it's not,
I'm so sorry, can you say it again?
it's not head on, your eyesight isn't head on, it's off-center or offset by 3%.
Yeah, knock on the table. Other opinions? If I have my phone on in front of me, if I want to make this experience a little bit cooler, I was turn on my flashlight and just blind myself, but I'm skipping that part. So if I'm looking at the screen, I'm seeing my entire screen, right? The moment I start tilting it, I might not feel a difference, but actually I'm seeing probably a little bit less of it, right? And the moment I fully tilt it, all the way to where cos alpha becomes 0, tilted completely, I'm looking at the side, I'm seeing nothing, right? And that means why I call it that cos alpha is 0, if it's fully on the side of my eye level. Does it make sense? That is what we have, that idea of projected area. That's what it means. The rest of it, again, back to what we had. You have everything from the question. Just plug all those numbers in. You have the surface. You have cos alpha. Plug everything in. You will have 354 candela. Just too important not to forget what that cos alpha is. First question. The next question is this. You're looking for illuminance on the panel's left face. To solve this question, you need to assume the panel, something is hitting the back of this panel, and there's a tau involved, and there's something leaving it called M. So you got EM and tau. He's not in the question, right? You're just assuming that. Once you assume that, the rest of it is just very easy. The M, you have the pi, you have the L. Very easy. Multiply them, you will get the final answer. The reason we have this Lambertian surface here, or Lambertian, I don't know how you pronounce that, but it's Lambertian. I think I forgot to check it. Is it Lambertian? Does anybody? I think it's Lambertian. For the Lambertian surface, you have this very established equation. That's why it has to mention that in the question. And once you have that, again, this is just plugging in all these values. You have M calculated from there. You have the tau from the question, which is up here. You just plug in those in, and then you find your E, which is essentially what the question asks. Yes.
So for Lambertian surface, you're saying it's the bottom of where you have lines in that surface?
Yes. Yeah, that is the established equation for those kind of surface that it exists. If it's not that surface, it's going to be a different thing. You're welcome. Any other question? All right. Clear all drawing. There we go. Perfect. Now, this is also a very fun part of it. You got the luminous flux hitting the left side and the right side. You just need to calculate this part of things. You have the surface area of both. You have E and M from the previous part of the question. Plug those numbers in, you get the final answer. Before we move on to the next question, which is the interesting part of this entire problem, is that, again, the important thing with lighting question is to have that solid foundation when you're starting to solve the question. Once you have that, you're ready to go. The rest of it, literally plugging in the numbers. That's it. All right. Now we go to the fun part of the things. We're looking to find E on surface B. Right? If I am the viewer, my eye will be looking at this surface, and I have the normal of the surface. If I am surface B, it's no longer a viewer. What you're essentially dealing with are two surfaces. This is very random. I have a phone. Don't assume that I just brought it for the tutorial. It's just randomly. I sometimes have a second phone. But anyways, the idea is that the first surface has a normal, right? This surface also has a normal. If they're facing each other, no problem. But if surface B starts to tilt, then the normal of surface B is going this way. The normal of surface A is this way, right? Alpha was my eye's difference in angle between the normal of the surface and my eye. It's on the viewer. We have this new concept of beta, which is the difference, or the angle, not difference, the angle between the normal of the surface A and normal of surface B. Does it make sense? So alpha is the angle between the normal of the surface and my eye, which translates to this one. And beta is this one, the difference between the two normals. Does it make sense? That is the key to solving this question. You notice, you get this right, you're done. You're perfect. You're ready to go, right? Because the rest of it is literally plugging everything. So E equals to I multiplied by cos beta. This I is extended to LA cos alpha, right? And this is cos beta. And then you got the D2 at the end, which is part of this first equation. Sorry, this cos alpha, you need to, this is, just ignore that for a second. Okay. So in this question, now here is where it gets interesting. Sometimes people mess up this alpha and they come up with an answer of 0 for the question, and that's how they lose marks, right? The important thing is to understand that your alpha is 0 because the surface B is directly working with that light, right? It's on the normal of that surface. The normal of the surface is hitting surface B, right? Back to showing it with the phone to you. This is the phone. This has a normal. If my eye is here, my eye is not hitting the normal, so my eye has an angle between my eye and this normal, which is 45 degrees in that question. If I want to be more accurate, I'm standing here, as you know, I'm showing something to my friend, my eye and the normal, the difference, 45 degrees, okay? With the surface, it's similar if my eye was here, but now the difference is that you got the surface there, the alpha is 0, but the beta is different because the surface is tilted. So the normal of this surface is tilted. And that is where we form the beta. Does that make sense? Okay. If that is clear, then we are ready to move on. We get the beta, which is 30 degrees. You got the L, you got the D, plug in all the numbers, and you will come up with the final answer, which, oh, we don't have a final answer. Got to put it on the screen. Anyway, oh yeah, there you go. We got the 12 locks here. Once you plug in everything. Does it make sense? Any questions? Those are essentially the problems that we were going through for today. And because you're engineering, I'd like to end this with science can amuse and fascinate us all, but it is engineering that changes the world, right? It's us that we are shaping the future, every single one of us. With that, thank you so much. That is the examples. I can give you a 10 minutes or 15 minutes break. Don't get excited. You're not going home. It's probably one of those tutorials that's going to even last a little longer than the session. I'll try to get it done on time. You're going to go through one of the tools once you're back. And let me just finish this thing. Recording, stopping with the recording.